This is MATD 1534, and we start with Unit 11 today, the quadratic and rational inequalities. This is a very, very important topic, and sometimes people struggle a little bit with this, so let us do our best and see if if we don't, if we really go through this proper, if you don't understand this and do a proper answer for questions here. Now, the first thing that I just want to say, inequalities in itself is sometimes difficult to understand, because if I have like x plus 2 is 5, it's easy to answer that because x is can only now be 3. It's unique. It's a unique solution. But the moment that I say that x plus 2, for instance, is greater than 5, then suddenly this changes to an infinite number of answers, because now x must just be greater than 3. So any number that is greater than 3 will now be a solution, making it an infinite number of solutions. And the concept of that, the grasping of that something can have an answer that is like infinite, that is already a difficult concept. And how do you put it on a number line? How do you present something that is infinite? How do you present an infinite number of answers? So that is why we started the year with those the graphs that we did on the number line, the indications, the inequalities that we've done on the number line. So now we're going to need our number lines. And you will remember when we did those number lines, just indicating inequalities on a number line, that I said we are doing this because we're going to need it a bit later on. And now we are here in Unit 11, and now we're gonna need it. So I'm going to now take an approach that is a little bit different than the normal way that people are doing this. So I just want to state again here, we're talking here quadratic and we're talking rational inequalities. That's also important that we just understand that. So quadratic, we all know now, it's the quadratic equation, the squared x squared and so on, ax squared plus bx plus c, the parabola in other words. Rational, we know, is a fraction. So these are fractions. These are like hyperbolas. So, but remember, it's inequalities now. So these will be fractions. So just before I go on, I just want to say another thing that is very important, and that is something else that we must understand. If we have that the number 3 is greater than the number 2, that is fine. But the moment that I multiply with a negative, then I have minus 3 on this side, and I have minus 2 on that side. Now suddenly, this minus 3 is not greater than minus 2. It's actually less than. So that is why we say if we multiply by a negative, the sign must swap. But this creates tremendous problems. Because if I now have, for instance, that 2 over x is greater than 5, you see, now I cannot go ahead and just multiply here by x, which is the common multiple, and say that 2 must be greater than 5x. So times by x times by x. I cannot do that. You see, that's the problem. Because why can I not do that? Because I don't know what the sign of this x is now. If this x is positive, this will be fine. But what if this x is negative? Then the sign is supposed to swap, and it never did here. So that is why this is critical that we understand what we are doing here, so that we don't fall into traps like this and then our solutions are totally wrong. All right, so we're going to follow an approach which we call the boundary points approach, which will help us not to fall into that trouble. So the boundary points just tells us that where something can change, something can go wrong. So for instance, this x here cannot be 0. So that 0 will form like a restriction, and the boundary points I'll discuss a bit later. But just understand that we will have to look at our boundary points and we will have to look at our restrictions. Okay, I'm just going to move on here so that I can just start with an example. I'll explain then all that other uh, things at the top there, the boundary points and so on. So if we look at this number A, just to start off with this number A, this is now a quadratic inequality because it's quadratic in form here, and there is an less than sign, making it immediately an inequality. So what we do now is we change that and we go find the boundary points. The boundary points will be when this is equal to 12. But what I do is I tell the people, listen, I'm busy finding out the boundary points. I'm not doing any solutions yet. This is important that you state this, that you tell us that you are doing the boundary points. You're just working out the boundary points. You are not now giving any solution. Because remember, if this is less than 12, you cannot give answers like equal to, because this is an inequality. The answers cannot be equal to that. You're supposed to give answers less than 12 there. So when you put x in here, substituted back into here, you should have less than 12, not equal to 12. So the boundary points will be when we put our equation then equal to here. And then we work out these boundary points. And then what we then do is we go to our number line, as I indicated there, step 2, and we put these points on our number line. All right. And now, step 3 is very important. I know there's many ways people look at these sums. They will do the little parabola and say, okay, that's where it's positive, that's where it's negative, that's where it's positive, etc. A very good method. No problem with that method. But guys, I can tell you now from my 30 plus years experience that people fall into trouble here. So I still believe the best way is to do what I'm showing you here now. So what we do is we get our number line ready, and then on it we put our boundary points. So the points that we just worked out above. Let's go just back. We see it's 1.5 and -4. So here it is. It's the -4 there. There's the -4. Let me do it in green that you can just see. There's the -4, and there's the 1.5. But indicate it here. Indicate -4 and indicate your 1.5 or 1.5 or 3/2 or whatever you want to do. And then we can clearly see that this number line is now broken up into 3 regions. We have to the left of this boundary point, we have in between the 2 boundary points, and we have to the right a section or a region to the right of this boundary point. So now what we do, and as I say again, it still is the best, I think, way to do this. This is a very simple example, and you might feel now, no man, this is not necessary. Remember, we start here just to introduce the method now. So you can go quicker here, of course, but this is just an introduction to the method. So what we do in step 3, we will rather take points in the regions, and then we will see if it makes the equation true or not. Remember, this was our equation. 2x squared plus 5x must be less than 12. So now I take any number in region 1. I decided to take minus 5 because that is a number in region 1. I substitute it and I check. And I see 20, I get 25, and that is definitely not less than 12. So this makes it false. This makes this false. So region 1 is false. Okay, so there's no solution there. Then I take a number in the second region, 0. I took 0, but you can take any number in that region. You can take -3, -2, -1, even -1.5, uh, 0.5, any number in that region. And you test again, and you see now you get 0. Well, that is definitely true. 0 is less than 12. So this region 2 is true. I have solutions there. So this region, remember we talked about infinite number of answers. So this whole region will be then giving me answers that will be true. And then I take any number in the third region. Okay, I took 2 here for this example, but you can take any number in that region, test it again. Mine worked out to be 18. That is not greater than 12. So this is false again, telling me that region 3 is false. Therefore, the answers that I must give must be the ones that is true. And therefore, the true will be, as we said, in the region between -4 and 1.5. Here you can see the indication of this number line now. And remember that it was just less than, so therefore not included. So we can put it with this brackets like that as we've done it earlier in the year. You will remember that. Or we said you can put a little hole there and a little hole there to show that it's not included. And then you can indicate that your answer will now be between -4 and 3/2. This is the set builder notation, and here's the interval notation. Remember, we go for the interval notation mostly, but we will have to read what the question asks us. If the question says give it in set builder, then we will go for the set builder. Otherwise, we just give our answers in the interval notation. Okay, just before I go to number B here, let me just go back here. About these tests now, you can see this is a lot of working out here. You do not have to show it. You do not have to show it at all. You must just do that. Remember, we're just interested in which regions are going to be true. So you do not have to show any of these tests. I did it here thoroughly for explaining what we do. But you can just, when you have your boundary points, you can set up your number line and you can do your test and you can determine where does it false and where is it true. And then you can just write down your answer. You do not have to show all these working out for me. As long as it's just been done and you can find the regions that is going to give true answers. Okay, so that was a very simple example. Let's go for one that is maybe a little bit more advanced, also not really difficult, but I mean there's a lot of factors here. We have x minus 2, x plus 4 squared, and x minus 4. And now, remember these already in factor form. So I do not multiply out here because I can find the boundary points here immediately, because the boundary points is just what's going to give me is the values that's going to give me equal to 0. It's going to make, remember we said boundary points is where we put the equation equal to 0. So I'm just going to tell everybody, listen here, I'm just busy finding the boundary points now. I have not indicated it in the book, but when you answer this like in a test or in an exam, indicate that you are working out the boundary points. You're just busy finding boundary points. You're not um, calculating the inequality at the moment. So clearly we can see 0, 2, -4, 4. In other words, those are the 4 boundary points now. So now we go put them on a number line. So there we did it. It's -4, it is 0, it's 2, and it's 4. There's the 4 boundary points now put on a number line. -4, 0, 2, and 4. Breaking the number line up into 5 regions now. So now I have to go check where is it true and where is it not true. So I go to my -5 and I check and I see I get -315. Well, that's not greater than 0, so this is false. Then I go to -1, any number in the region. This is -135. Well, that is also not true. Then I go to my next region. I took 1 there, and I got 75. Well, that is true. So my third region is going to give solutions. That's going to be solutions. When I go to x is equal to 3, in region 4, I see it's false again. And when I go, I took 5 in region 5, and I see, well, that is greater than 0, making it true again. So here is my next region that I will have true answers in. So coming here below, we can see I've indicated now that's going to be true, and that's going to be true. So it's between 0 and 2, between 0 and 2. I've indicated here in the interval, there's the set builder, or greater than 4, 4 to infinity. That will all give me true answers now. Once again, I do not have to show any of this, as long as once I've founded my boundary points, I've put them on the number line, and I understand that I have 5 regions, and then I test the 5 regions, then I'll be fine. All right, let's do now one that's a little bit uh, different here. So now I have x squared plus x minus 4. Example actually 3 now. And now I see that there's no factors here. So I still go and do my boundary points. So I'm going to still indicate, listen, I'm going to first work out my boundary points here by putting that equal to 0. Well, we've done completing of the square. We've done the formula, etc., etc. So we remember that AC method also to see quickly that there's no factors. So I see there's no factors, so I go to my formula and I work out my boundary points. So now my boundary points is going to be minus 2.56 and 1.56. That's what I found the boundary points to be. Then again, I put them where they would be on the number line. Because remember, I just want to see the regions. I want to find the regions. And there's the 3 regions now. And now I just want to check inside those regions. So now I can make it easy for myself. I can choose any number there. So I did -3. I don't have to work with that decimal, that irrational number now, because I'm checking inside the region. So I took -3 here, all right? And I saw that it's true. Then I go to the second region. I decided on 0. I saw that it's false because I got -4. And the question is actually, where is it greater than 0? So this is false. I go to the last region. Any number in there, I decided on 2. I could take any number in that region, and it's giving me true again. So once again, I have true here and true here. But remember now, it's included. It's included now. Therefore, I will have the square brackets here, the square brackets to indicate that it is now inclusive. So it's to the left of this one and to the right of that one. So I can also put it in my decimal numbers. I here just left it in the third form, but I mean, we can also write negative infinity, and that was, let's just check, negative 2,56. Where did we do the answer there? Yeah, negative 2,56. So all the way to negative 2,56 to 2 decimals, and it's included there. And then I can also just put a semicolon here for the or here, or the other region, or together with, that means together with the other region, and then that is at 1,56. So this is then included 1,56 all the way to infinity, because that region just goes on and on and on to the right. This one just goes on and on and on to the left. So those are the two regions that will have valid answers in them. Okay, so this is then the quadratic ones. We're going to stop today with the quadratic ones. We will do the rational ones next, but there's a reason why the quadratic ones comes before the rational ones. We need to understand exactly what we have done here. Otherwise, we're going to have problems with our rational inequalities. So this concludes now the examples for the quadratic inequalities.